also says that you are having large collecting area. So the bigger dish is the better radio antenna. So this technique is called as interferometric technique, and it has also won Nobel in physics. These two people, Anthony Harris and Martin Weil, they got Nobel Prize for this interferometric antenna innovation. So yeah, here you can see this is GMRT. It is situated at 80 kilometers from Pune. So here you can see that this is a single dish antenna, and there are few many others. So it is a Y-shaped array, and these all antennas are connected together. So that is how you get more resolution and also more collecting area. But yeah, like a full single dish antenna having the longest baseline of GMRT is 25 kilometers. So if you have a 25 kilometer diameter of antenna, it is always better, but that is expensive and not practically possible with all the artifacts coming in. So the interferometric techniques work here. And here is the OT radio telescope. And yeah, the low frequency array, low power array. So yeah, I find this like surprising kind of antennas because I haven't seen like omnidirectional in reality. So yeah, this seems unrealistic, but yeah, this is a low frequency array. It works at low frequency, while GMRT works at 50 hertz to 1.4 gigahertz frequency range. But this works at sorry. Okay. So this is a low frequency array which works at 10
Excuse me, ma'am.
40
कोण
million.
केला की उचललं
And this is VLA very large array. So this is also working at much higher frequencies, such as it can look up to 50 gigahertz in frequency range. So now that we have learned about radio telescope, we must also know if we are collecting the radio signals and processing it, what science is that part of spectrum telling us. So radio waves are not only coming from the hotter objects or energetic objects, but the radio waves are also emitted by cold and dark objects. And these objects are not really detectable in the visible part of the spectrum. So there are three processes happening in radio part. One is the synchrotron radiation. Synchrotron radiation is similar to cyclotron radiation. Uh, uh, unlike like the particles moving around in the magnetic field, they emit some radiation, and that radiation is seen in radio part. So, and this mostly does not depend on temperature. So, this emission is called as non-thermal emission, and most of the radio sources emit synchrotron radiation. Also, Bremsstrahlung radiation by hot gas is also observed in radio wavelength. Also, some other molecular transitions or atomic transitions are also observed as radio. So, these three processes, if we are studying radio signals, so we can say that these three processes are happening in some galaxies or some astronomical objects we are observing. So that is the science we can definitely get from radio signals. So these are few important discoveries that radio astronomy has given us. So first is this is a radio galaxy. So I will ask all of you to go and look after this lecture to see how this galaxy looks in the optical counterpart. So radio galaxies usually have a center core, and these are the jets emerging from it. These are the lobes, and these are the time relativistic jets emerging from it. But if you go and look and see it in the optical part, it looks completely different. So we cannot say that this whole thing is one radio galaxy in optical part, but in radio, this was the first ever
Ma'am,
discovery radio galaxy. And this was done by Grote Reber. He was also a radio engineer, inspired by the Carl Janssens work. He built a radio telescope in his backyard and he discovered this radio galaxy, Cygnus A. Also, the spectral line, which is H121 centimeter line, is seen radio. So, this line is the neutral hydrogen spin flip line. So, this H1 data of any galaxy, if you see galaxies in optical and all that, you can see that the size of galaxy is smaller in optical, but if you see it in radio H1 data, so you can see it has a much larger extent. So to know the true extent of any astronomical object of a galaxy, so you can look at the neutral hydrogen part. Also, this hydrogen is involved in star formation and all, so it can give us insights about star formation, other activities happening in the galaxy also. Yeah. So another one very important discovery was the CMBR radiation, the cosmic microwave background radiation. So we say that there are various models which say how the universe originated. So one of the models is the Big Bang model, and they said that Big Big Bang says that at some point in time, universe started to spread out. So expansion of universe started, and each point started moving away from each other. So, but at this part, the universe was extremely hot and dense. So can it did not form atoms and molecules and all that matter. So when forming atoms and molecules, so at this time, this uh, photons started coming out of the matter and it started spreading over all the universe. So it was the time when photons started moving around in the universe, but these photons had information about the early stage of universe. So this radiation is detected in radio part, and yeah, so it is evidence that Big Bang so far. Also, we can see some in the radio wavelengths, and we at different radio wavelengths, the sun is different. So if you go at higher frequency, you can see more detailed picture of the sun. And yeah, that is the thing. More, you go at high frequency, and you can see the most detailed astronomical objects. Also, there are few transition lines, few many transition lines in radio. So such as water, CO, and all that. And these transition lines, petrol lines, they have information about the star form region of the universe. So yeah, these lines also appear in radio, and yeah, so it's important to study all this. So the take home message for today is a single object can look completely different at different radians. So if you want to have a more diverse picture of an object or of the universe, so you have to look at that object using different wavelengths. Like you can use X-rays, radio waves, visible light to study the same object and you get different information. So that is why multi-wavelength astronomy is interesting. And like radio astronomy has been responsible for a great part of our understanding of the universe. Because before radio astronomy, we only like after people started looking at radio wavelengths, people also started to look at other wavebands such as X-ray or MRA. So now we have all sorts of astronomy. We have IR astronomy, we have X-ray astronomy. we have gamma ray astronomy. So this gives us a be looking at other wavelengths also, other for studying. So
Possession.
Is there anyone for say regarding today's
Yes,
session?
sir.
Please feel free to unmute.
Yes, sir. I'm having a question.
Yes, Nishaz.
Sir, how far is the galaxy from the Earth?
how far is the galaxy from?
The Earth.
Which galaxy from Earth?
Andromeda Galaxy and Milky Way Galaxy.
So we are a part of Milky Way galaxy. Our solar system is part of Milky Way galaxy, and the Andromeda galaxy is about 60 kiloparsec. 1 parsec is 3.6 million light years away. So yeah, multiply it.
Okay. Thanks, ma'am.
Is there any question for specific to radio astronomy? You can feel free to ask.
Yes, sir. Actually, I wanted to ask about here Mama told us about various type of antennas. So they told us about 25-kilometer long antennas. So is it at the dish? It is big or it is a line of dishes?
So are you talking about GMRT?
Yes.
So GMRT is it has 30 dishes of 45 meter aperture. It's placed in a Y-shaped array. So, and the longest baseline, the distance between the farthest antenna is 20 kilometers. So the longest baseline is 20 kilometers, and the longest baseline is how much